Hi, I'm Ben-Yaakov. This presentation is entitled How to Obtain the Output Impedance of Operational Amplifiers. There is a relevant video, this is the link to it, and I'm going to put it also at the page of this present video so you can click on it. We know that operational amplifiers have output resistances. Well, it could be actually an impedance, but in most cases it's just about a resistance, a pure resistor. And this information is not always available in the data sheet, certainly not for all operating points. Now, why is this important, this resistance? There are many cases you'd like to know it. For example, this output resistance will affect the stability of the system when it is capacitive loaded. That is, if you have a capacitor loading the amplifier, this is the internal resistance, then you have an extra phase shift and this could cause oscillation. So the objective of this presentation, of this video, is to show how you can obtain this resistance either by measurements or by simulation, if you have a model that will represent the amplifier, of course. Now, the first thing that comes to mind is to say the following. Well, let's show the input. Let's inject some current, could be directly or through some resistor with a voltage source. Measure the voltage here when you know the current. And then, of course, the resistance is the voltage time over the current. This is fine. But the point is that in practical cases, with practical hardware, you cannot do that. Because of the offset, the amplifier will immediately get into saturation. In fact, you cannot do it with in simulation, because most models will also have some offset to it, so that you cannot do it. In simulation, you can adjust the input just about to have a proper operating point. This could be done if the amplifier does not have noise model in it, because if there is a noise model, then this is going to be very, very noisy. So in case, however, you don't have a noise, you can just about by simulation stabilize the amplifier and then inject the current either directly or through a resistor and measure the impedance just by Ohm's law. And here I'm doing it by simulation. This is a PSPI simulation. Here is an amplifier LT1219. I found that minus 18 microvolt will bring this operational amplifier into proper operating point. Very important to look at the dot out file and see that you are at the operating point. And here we see that the input is minus 18 microvolt and the output is 2.44 while the power supply is 5 volts. So we are just about at the mid operation point. That is in the voltage is half the supply, which is very nice. And now I am injecting here 1 amp AC. This is going to be an AC analysis because I like to see the small signal, of course, as a function of frequency. Now, some might wonder how come that I'm injecting 1 amp. And obviously this amplifier is not capable of either absorbing or outputting 1 amp. Well, the point is that if you are running an AC simulation, the first step that the simulator would do is to linearize the system into a regular phasor type matrix. And in that case, it's not sensitive to amplitude. And so therefore it's very convenient to have 1 amp here, and therefore the volt here is actually the impedance that you'll find here at the output of the amplifier in open loop. This is entirely open loop. And here what I'm getting, at low frequency it seems that the resistance is about 60 ohms, and then it goes down at fairly low frequency to about 35 ohms. This is the resistance here, and this might indicate there is some sort of a reactive element involved in the model, so that you see this change. It's not a pure resistor. So this is the open loop measurement, which is nice, but as I've said, this is not practical to do in the lab. You cannot do it on hardware. So what are the other possibilities? There is one way which you can adopt, which is also good for simulation, and in fact you can do it by actual measurement on the amplifier. And here's the idea. If we look at the output resistance of an amplifier in a closed loop, and here it is just a case of beta equal to 1. This is the general case in which I have some network in between, so the loop gain is beta A. Okay, this is the loop gain. Now if I look here at the output, theory tells us that the resistance that I'll see will be Rs over 1 plus beta A open loop. This is very simple to derive, because if I have here a signal I am posing V sub S, then the signal that I'll get on the other side of the resistor will be minus beta A open loop Vs. So therefore the total voltage is 1 plus Rs Vs plus this, and therefore the current is this current, from which I can calculate by Ohm's law the impedance. I know the voltage across it, and I know the current. So this is therefore the output resistance of an amplifier or any feedback system, as a matter of fact, that has a open loop resistance or output resistance of R sub S. Now the interesting thing here is the following, that when beta A open loop is large, and this is the region that usually you like to operate in, this is the whole point of feedback, to have a large beta A, then in this case, it's larger than 1, R is divided by beta A, so therefore the impedance becomes very low or very small, depending on the magnitude of beta A. However, what is interesting to us is that if beta A open loop is smaller than 1, you get in fact Rs by itself. And the reason is that beta A smaller than 1 means that there is practically no feedback. And if there is no feedback, then you get R sub S as it is. Now, why do you like to have the feedback? You like to stabilize the system. So you can stabilize the system in such a way, with such a beta, that at higher frequencies, this beta will drop down, becoming beta A smaller than 1, and then you can then do the measurement and get the output impedance. And here I'm doing it by simulation, same amplifier, it's also piecewise. And now I've stabilized the operation amplifier to 2.5 volt, halfway. I have a feedback here. Let's forget about this. Let's assume this is a short here, so it's just a line here. I have here now a network between here and the point of feedback, so there is a beta here from the output until I get the feedback. There is a transfer function, and you can see that it's a sort of a frequency dependent function. We'll look at it in a minute. This is 10 meg, this is 1K, and this is 3 millifarad. And of course the transfer function will be this is 5. R5 was 1 over j omega C1. This is this one. divided by the whole thing. And here it is. So this is the beta. And for the values that I have, it turns out that this is the transfer function of beta. That it starts here at 1 over C R4, R5. This is in omega frequency. You have to divide it by 2 pi. And then it goes down 20 dB per decade at this value. So now we have the open loop. We have this beta. This is the beta, sorry. And when I multiply the A open loop by beta, this is now the transfer function of beta A open loop. And obviously, depending on the shape of this beta, I can cause this crossover frequency. This is where beta A open loop, should be 1. This is 0 dB, okay? That's 1. It's in dB 0, but beta A open loop is 1. Then I can shape this beta such that this crossover will be at low frequency. So from this frequency and up, we have a beta A smaller than 1. It is important, though, to make sure that the crossover is such that you have a phase margin which is reasonable, so the system will not oscillate. Okay? I'm not going into it. I have a number of videos that are discussing it in my YouTube channel. You're welcome to watch them. So this is something to worry about, to make sure that you have a decent phase margin here so the system will not oscillate. So here we have it. We have the amplifier stabilized to 0.5 volts. We have the beta here. And here I'm preparing a current source to measure the impedance. But before that, I have here a voltage source, an AC voltage source, in order to look at the beta A open loop, at the loop gain transfer function. By putting this source here and then looking at the ratio between the voltage here and the voltage here, you get the transfer function. This is something, again, that is discussed in some of my videos. And just going over it very briefly, you can understand it by the fact that if you have a signal here, you go all the way to here, all the way to here, and then back here, so the gain between here and the loop here is indeed beta A. So if I take the ratio between the voltage here to the voltage here, this is beta A. I can do it very easily by simulation. Here I've put here 0. This is 1 volt, could be any number. 1 is kind of convenient. And here it is. So what I'm getting here is that beta A indeed is going down, and it is crossing here the 0 dB, beta A equal to 1, at about 20 hertz. So I expect that from here above, maybe a little bit less, beta A becomes smaller than 1, and then therefore when I inject the current at the output, I'll see the open loop impedance. And here it is. This is what is obtained here now with the method of stabilizing the loop. This is the region that the method works. From here to here, this is beta A smaller than 1. Here, beta A is larger than 1, and this is why we see an impedance which is much, much smaller. We'll see it later on. And here I'm comparing it to the open loop impedance or resistance that I've measured before by simulation, open loop, stabilizing just by an offset at the input, the amplifier to midway. And as you can see, I get here 35 ohms and here 35 ohms. Here, this is the actual behavior of the resistor, or impedance I should say. I don't see it here. This part is correct. This is not related to RS, this is just RS over beta A open loop. And this is just a log scale here, just to show that indeed as beta A open loop is high, we get lower and lower values for the R out F. This is the output impedance with feedback. Now let's have a look at another method, which is kind of neat. And here's the idea. We know that the output impedance with feedback or under feedback is RS over 1 plus beta A open loop. So for the range that beta A open loop is larger than 1, and this is the useful range, then if I multiply this by beta A open loop, and if 1 is smaller than this, then it drops down, and I'm getting that this product is in fact the closed loop RS. Okay? So for that, I need two things. I need the impedance under feedback, R out F, which I can measure by injecting an AC signal at the output in closed loop. And then I need the beta A open loop, which I can either measure in the lab, in fact, or by simulation. So let's have a look at it here. In order to make things simple, I've just put two circuits. One for the measurement of the R out F, that is the output impedance under feedback. Here is a 1 amp current source. This is not operating. This is like a short. And here, this doesn't work, and this operates, and this gives me beta A open loop. So if I multiply the beta A open loop that I have here by the R out F, the output impedance under feedback, I should get RS by itself. So let's see how does this work. Here is beta A open loop. Now this is feedback of 1. So basically beta A open loop is the A open loop of the amplifier, because beta is equal to 1 here. So this is now beta A open loop. This is what I measure by simulation, the output impedance. Well, you can see very nicely that when beta A open loop is large, then the output impedance is very, very small, because it's 1 over beta A. And then goes up. As beta A open loop goes down, the R out F goes up. Now the product is here. So this is the region that is of interest here. And in fact, this is also. So this is now the output impedance, RS, for the case that you measure it, everything under closed loop, by knowing both the output impedance under feedback and beta A open loop. Very nice. See it here? By the way, as I've noted in the earlier video, which I've linked here, although I'm using here the same amplifier as I've used in the PSpice, the performance of the model is a little bit different. So the models are not exactly the same between PSpice and LTSpice. And therefore the value of the output resistance is also not exactly the same. You see here that the output resistance here is about 100 and something, while earlier with the PSpice we got it to be 35. Okay? So the models are not exactly the same. This is something to remember when you're using simulation. So let's go back now to the point. We have beta A open loop, we have the output impedance with feedback, we multiply, and we got the result. And now I'm going to compare it to the other method, or the earlier method that I've shown, in which there is a stabilization of the operating point, such that the crossover frequency of beta A open loop is at low frequency. So therefore, at a high frequency, you actually, by injection here, you can get the open loop resistance. And this is what I'm getting. Now, this is not the correct region. This is the region which is correct, because this is the region where the beta A is already lower than 1, smaller than 1. So this is the open loop output resistance. And now I'm comparing this with the earlier method that I've just shown, that is multiplying beta A open loop by R out F. And lo and behold, we see everything comes together. This is what I've measured with the stabilized operating point, and of course the crossover is somewhere here. So therefore, this is the region when the result is correct, and it coincides with the region with the value that we got by multiplying beta A open loop by the output impedance under feedback. Obviously, this is not correct, this value here. Here, while this is okay, because we got, as long as beta A open loop is larger than 1, then the multiplication here is pretty good. So this brings me to the end of this presentation. I hope you have found it of interest, and perhaps it'll be useful to you in the future. Thank you very much.